Okay, so now the natural question is, okay, it's great that the margin of error went down, but let's say that you know you want to tolerate a maximum or a margin of error that is at maximum 1%. So you don't want a margin of error that's 3%, you want a margin of error that's only 1%. So you know that to bring your margin of error down, your sample size needs to go up. So the question is, how much does it need to go up by? So again, now instead of a margin of error of 0.03, you want 0.01. And you know your sample size needs to go up. So how do you think you can find the appropriate sample size for this margin of error? So your margin of error is calculated from this expression. You know that that needs to be 0.01. How do you find the sample size that's needed? Yeah, very good. So one way is that you can repeatedly guess and check, right? You can say, oh, I know that the sample size needs to be bigger than 1,000 for my margin of error to be lower than the previous 0.03. So I'm just going to try different numbers. Like I'll try 2,000 instead, and plug in 2,000 here, crank this out, and see what the margin of error is. And if that doesn't work, keep increasing the sample size so that you get a margin of error that you want. But that's repeated guessing and checking, and that's very cumbersome. And we know that we can do better than that by setting this whole expression to the margin of error that we want, which is 0.01, and then solving for the sample size. So let's do that together. So we know we want the margin of error to only be 1% in either direction, or 0.01. And we know that this margin of error is coming from this formula. I'll just write out the formula generically first. So let's go ahead and plug in what we know, and we'll solve for what we don't know. So we're trying to solve for n. Let's plug in everything else. So what would the z-score be in this example?
1.96.
Yeah, so it's dependent on the confidence level that is given, which is 95%. So the z-score based on that confidence level will be 1.96. So what do you think p hat would be?
0.371.
Yeah, the 0.371 is based on this particular sample of 1,000, where it ends up that you're observing for that sample 0.371. But here, we haven't even collected the sample yet. We don't know what sample size is needed. What if we need 10,000? Then this may or may not, the p hat observed may or may not be the same 0.371. And it probably likely will not be this answer. So the short answer is we actually don't know what this p hat is, because we haven't observed that sample yet. So it turns out that if you don't know what p hat is, we're going to use 0.5. And in a little bit, we'll talk about why we chose 0.5. But for now, if you don't know what p hat is, we're going to choose 0.5. And if p hat is 0.5, then what do you think q hat is? Yeah, so q hat is the complement of p hat. So if p hat is 0.5, q hat will be 1 minus 0.5, which is 0.5. And then this n is a sample size that we don't know. And that equals this margin of error that we desire, which is 0.01. So let's review some basic algebra together. If we have this equation, and we have this unknown n, what's the next step that we could take? What can we do to both sides of the equation to get closer to getting n by itself?
Divide both sides by 1.96.
Yeah, good. So we can make it a little bit simpler on the left by getting rid of this 1.96. Right now, we're multiplying by 1.96. We're going to undo that by dividing by 1.96. We're going to do it to both sides of the equation. So over here, we have this, and if we divide by 1.96 on the left, we're going to undo that, and so we just get this on the left. So now we're a little bit closer to getting n by itself, so what's the next step to getting closer to getting n by itself?
Square both sides.
Yeah, good. So right now we have the square root. We're going to undo that by squaring that, and so we're going to square both sides of the equation. So what might be the next step to getting closer to getting n by itself?
Times both sides by n and then divide both sides by the entirety of the right.
Okay, very good. So right now n is stuck on the bottom of the fraction. We might want to get it on top rather than have it stuck on the bottom by multiplying by n on both sides. If you multiply by n on the left, you're going to divide out the n, and it's no longer going to be on the bottom of the fraction. And then on the other side, n will be multiplied. So we're going to multiply by n on both sides of the equation. And then the only thing from keeping n from being by itself now is it's being multiplied by whatever this number is. So all we have to do now is divide both sides by that number. So dividing is just multiplying by the reciprocal. So we're just basically going to flip this number and multiply both sides by the flip of that number. So we're going to multiply both sides by 1.96 divided by 0.01, the whole thing squared. And this turns out to be the sample size we need for this desired margin of error of 1%. So go ahead and calculate this, and we'll talk about the result.
N should be 9,604, right?
Okay, good. So if you punch this in, this should be the answer that you get, and it should be 9,604. It turns out that you get this exact nice whole number. But let's say, hypothetically, we had gotten a decimal, like 9,604.2, and that represents n, which is the sample size needed. So you know that you can't get a fractional number of people to represent n. So do you think we should round up or round down? So however we round should reflect the number of people we actually need to sample in order to get a margin of error of 0.01 or less. If we get any margin of error that's less than this, that's even better. So this is saying that we need exactly this number to guarantee this margin of error, but if we round down, then you know that a smaller sample will give a larger error. Then if we round down, we're at risk of getting a larger error than this 0.01 that we want. So we need to round up. So any decimal number that you get for the sample size, you need to always round up.
Sorry, how do we get the 0.62 to the other side after multiplying n?
0.62 to the other side. 1.96?
Yeah, how did we get to the other side?
Right now, this quantity is being multiplied by n. So
Yeah.
to get n by itself, we're going to divide both sides by this number. So dividing by a number is the same as multiplying by the reciprocal. So the reciprocal is this number flipped. So we're just going to basically multiply both sides by the reciprocal of this number, which is the number flipped, which is 1.96 divided by 0.01, the whole thing squared.
Okay, thank you.
1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1 So if we have a decimal number, you always round up. But in this case, we're lucky we got a nice whole number to begin with. So the sample size that we need is 9,604. So this is the number of people that we need to guarantee a maximum margin of error of only 0.01. And if you have more people than this, even better. Your margin of error will be less than 1%. So let's generalize what we just said. So we saw that this sample size came from this equation, but these numbers were specific for this example. So let's generalize it for all other examples. So this 0.5 here and this 0.5 came from which of these variables?
P hat and Q hat.
Yeah, p hat and q hat. Remember, these are directly observed from the sample, but because we haven't even observed the sample yet, we have to use 0.5 for p hat and likewise 0.5 for q hat. So what does the 1.96 represent? Yeah, the z-score for that particular confidence level. So this is the z alpha over 2. And what's the 0.01 represent? Yeah, that was the desired margin of error. So that was the E. So this is the formula to find the sample size that is needed for a certain given margin of error. So it'll be p hat times q hat times this whole quantity squared, where the quantity is this ratio, z alpha over 2 divided by E. So writing that out again, it will be, and is p hat times q hat times the z-score divided by the margin of error, the whole thing squared. So this is the formula that you'll see in your textbook and in your formula sheets, and it's nothing more than using a little bit of algebra on the original confidence interval formula and solving for n, the sample size. Any questions? Okay, so now that we talked about the sample size is coming from this formula, basically, this formula is basically saying that n, the sample size needed, is basically a product of this p hat times q hat, which is just the number, and then times whatever this is, and that ultimately will be a number. So the sample size is really a multiplication or a product of these two quantities. Now, if we this second quantity here, the z-score divided by the margin of error, the whole thing squared, that's going to be fixed in this situation, because the z-score is based on the confidence level, that's a fixed number, and the margin of error that you desire will be a fixed number. So this whole thing will be just a constant, that will be a fixed number. So the question is, if you take this product, p hat times q hat, and you were to increase it, then what happens to n? Does it increase or decrease? So in other words, if you had, let's say you had x times a fixed number. Let's say that equals y. Let's say the fixed number is 5. And so you have x times 5 equals y. If x is 2, then what's the value of y? 2 times 5, which is 10. And if you were to increase x to 3, then what happens to y? compared to what it was previously. It also goes up. So if you're to increase X, Y also increases. So same thing here, if you have this quantity, P hat times Q hat, and it increases, then N also increases. And so you know that you want to find the sample size that is needed for a certain margin of error. And you know that the larger the sample size, the better. Because the larger the sample size, the smaller the margin of error will end up being. So the larger the sample size, the better. So basically, if you don't know what P hat and Q hat are, you want to choose them so that this product will be as large as possible, so that the sample size will be as large as possible. So now the question is, what value of P hat and Q hat should you choose so that this product is as big as possible? So if you're to explore a little bit, let's say that P hat were 0.1. In that case, what would Q hat be?
0.9.
Yeah, 0.9. And what would this product, or this multiplication end up being? 0.09. So the question is, can you pick P hat so that the resulting product, P hat times Q hat, is bigger than 0.09?
Yes.
Yeah, and the question is, what should that value of P hat be so that this product is as large as possible? And it turns out if you play with different values, if you try to list out all possible values, if P hat were 0.7, then Q hat would be 0.3, and this product, P hat times Q hat, would be
0.21.
0.21. And the question is, can you pick a P hat so that the product is even bigger than that?
Yes.
And the answer comes from picking P hat to be 0.5. So P hat would be 0.5, and Q hat is also 0.5, and this product becomes 0.25, and it turns out that this is the biggest possible product that you can get. And the value of P hat that achieves that is 0.5. So that's why we end up picking 0.5 for P hat when we don't know the actual value of P hat. So that this product will be as big as possible, so that the sample size will be as big as possible, and to make sure that the margin of error is either 0.01 or less. Any questions so far?